Hello, everybody, and welcome to another DevHeads Meetup. Today is Friday, January 24th, and today is another engineering hour. We're going to continue our series on SEGGER tools today, looking more into SystemView. After last week, we looked at the real-time transfer functionality that you can use for advanced debugging. And of course, the expert in this case is Umesh Lokhande. Umesh is going to be taking us through this and another session next week as well to round out this sort of triple threat that he developed around debugging with SEGGER tools. So if you're into JLink or just getting started with JLink, this is a great series and a lot of useful resources here and in the DevHeads community. If you're not familiar with the DevHeads community, you can join us at https://discord.gg/devheads and find us there. Some feedback. Is that from you? Umesh, do you hear the echo?
Yes,
Let me see. Maybe it's
I'm getting echo, Brandon.
a Discord thing.
Yes.
Let's go. How about now? Yep, I think it was a Discord thing. Okay, well, sorry about that for everybody. So we're streaming in Discord too. So everybody over there, say hi. Let us know that you can hear and see everything, and we will do our best to take care of you and make sure you have a good event. So for those of you who are in the Meetup platform, if you have any issues during the event, at the bottom left of your screen, there's a little help button, and you can use that to sort of troubleshoot on your own. And then, of course, if anything comes up that you need help with, like if that won't solve anything, feel free to message me in the chat at Brandon Lewis. I just messaged there. You can see the chat at the very bottom right of your interface. There's a little chat icon. Navigate to that, and then you can just ping me and let me know if there's anything that you need help with. And I'll do my best to make sure you get back on track. Feel free to add questions in the chat, or just to the left of it, there's a questions tab. So you can put any questions you have for Umesh. He's going to be going for about 45 minutes, and then we'll have about 10, 15 minutes at the end for Q&A, where he'll answer any of the questions you have that he can answer. And same thing over in Discord. If you have questions or need help or anything, just use the chat channel that's there, and I'll do my best to assist you with whatever it is, and I'll make sure that your questions get migrated over here to Umesh as well. One last thing before we get started, I'm going to be uploading the presentation files into the platform, so you'll be able to navigate to those, and I'll give you instructions. There's a icon down at the bottom that says apps, and then if you click that, then roll up to handouts, it'll be there momentarily. So other than that, I don't want to take up more time. You guys didn't come to hear about administrative stuff about how platforms work. You came here to hear Umesh talk about SEGGER and the tools that they have for the embedded debugging. So with that, I will hand it off to you, Umesh. Take it away.
Hi, Brandon. Thank you. So I hope every one of you is excited to learn about a system view, and we will be exploring today how we can use a system view to record and visualize the real-time embedded system. So I will be using an STM32 microcontroller, and I have built an FreeRTOS application that we will be analyzing. So the agenda for today, we will first start off with an overview. Then I will talk about how the system view works, basically more of like why we need system view in the first place, and then what is system view is capable of doing and what it is exactly. And then we're going to talk about recording modes. There are two ways we can collect the debug information from the system view for the system view, and that's a single shot mode, and another mode is a continuous mode. And then I will show you how to integrate a system view source file into our STM32 microcontroller project. I will be using STM32Cube IDE for this. And then I will show you how we can export the SVDAT file from the debug window. This will be very interesting. I haven't seen anywhere online a detailed explanation about it, or maybe a step-by-step guide, and it will be interesting for you to see. And then I will show you a live demo where we will record, visualize, and analyze the FreeRTOS task in a real system. So I will show you live everything. And then we'll summarize everything that we have seen so far today. And then towards the end of the session, if you have any question, you can ask me. Feel free to ask me. If we run out of time in the end, then feel free to drop your question into our Discord server, and there are a lot of different experts out there. They will be very happy to help you. Okay, so why we need a system view in the first place? So if we use a regular debugger in general, then we have very limited insight. So the debugging basically is known for, you can put up the breakpoint, you can step through the code, then you have a watch windows, you can have a live expressions, but basically all what you can do is just to see what is going on with the variables, or the maximum you can do is to trace a little bit, you can graph here and there a little bit, but nothing more that you can do. So because we have very limited insight using a regular debugger, we need something more. Then to make sure, if we build a real-time embedded system and we want to make sure the performance is as designed, so when we build an application, we have something, some objective, some expectation from our project to match a certain timelines and deadlines, especially in the RTOS-based application, and we have to make sure that, and we need some sophisticated tool where we can analyze and record the data. And there are a lot of different ways you can use this recorded and trace data. Even it will be used for certification, your product certification later, but that's pretty advanced stuff. So just to make sure the system perform as we designed, we need something more like a system view. Then we can track down inefficiencies by analyzing recorded traces. So what happens is when you are analyzing and a task or your embedded system, I mean real-time embedded system, then if you know something somewhere is not right or something inefficient code or something that's there, you can remove it or you can optimize it better. But for that, you need to know what's going on inside your real-time embedded system, and that is possible using a system view because we have a visual information, everything. And then we can get a real-time visualization and runtime behavior. The great thing about it, yes, it's a visualization, it's a real-time runtime, but the great thing is it doesn't hamper, or maybe I could say it doesn't impact the microcontroller core when you perform all these things in a live real embedded system. And I will show you, because we will be looking into single shot mode as well as a continuous mode for recording the data. Now, let's just talk about what is a system view. It's a tool for visual analysis of an embedded system. That's what we talk about. And now maybe the question comes like, what kind of microcontroller it supports? Like what kind of architecture? So it supports ARM Cortex M, Renesas RX, or even some of the RISC-V architecture-driven microcontroller it supports. So I would pretty much frame it this way. Any microcontroller which allow you to access the background memory, access the memory in the background, you can use that. Otherwise, I would put it this way. Any microcontroller which can be used with an RTT technology of a SEGGER, then you can use a system view also with it. Okay, we'll talk about it a bit later, but don't worry. A lot of many popular microcontroller, they do have in support. Also, it support interrupt tracing for bare metal as well as RTOS based application. The great thing is it support bare metal code as well. I took it example RTOS application because I've been building a lot of this sessions of engineering hours built on the top of free RTOS sessions, right? If you go back to DevHeads YouTube channel, you probably will see a lot of free RTOS videos been made already. So because to keep the continuity, I used it free RTOS. But even if you have a bare metal code, if you wrote a complex embedded application where you have a lot of different interrupts and you want to track these events and interrupts, that's also possible. So system view can also works with the bare metal code, which doesn't have any operating system at all. So you can use it with an OS and without OS. So that's a great thing. And what else we can do with system view? So we can capture the task, we can capture interrupt, as I said before, then we can have a software timer information, we can have a user events that we can log, then we can log the API call. If particular API call is important for us, we can log that API call. We can even, interesting part is we don't just visualize it, but we can also set the triggers, okay? And we can track down that event or particular API call, and other microcontroller resources can be tracked. Now, let's just understand how system view works. So let's say this is our microcontroller. I will be using an STM32 microcontroller today, but the way we want to use microcontroller in this application is we want to use the microcontroller to collect the debug information. And then we have a jailing debugger, which will be used to extract the information from the microcontroller. Now, the debug information will be collected into the microcontroller using a system view API. And the data will be extracted by jailing debugger from the microcontroller that uses an RTT technology. So basically, if you remember, if you have seen my previous RTT engineering hour, then I spoke about it. If we have a microcontroller and if we connect a J-Link debug probe, then J-Link debug probe automatically detects the RTT control block. So it will pull the data, it will extract the data from the microcontroller, that debug information, then later further will be send it to the system view, which is our host application. And on this host application, we will analyze and visualize all the data in a graphical format. It would be amazing, by the way. So this is how the microcontroller will collect the data using RTT, I mean using a system view, and then using RTT technology, we will extract it and we will definitely use it with the J-Link debugger and then send it to the system view. This connection will be over USB to connect the J-Link debugger to the system view, at least in our case. So let's just talk about the connection detail, how the connection that I have shown in a previous slide will be realized in the real connection, real world. So let's say I have here an STM32 Nucleo board, and you probably know that STM32 Nucleo board has an ST-Link debugger on the board itself. So this part is an ST-Link debugger. If you buy Nucleo board, then by default, this debugger is set as a ST-Link debugger. But if we can install the J-Link firmware onto this chip, if we swap the firmware onto this controller, then we can able to convert this ST-Link debugger into the J-Link debugger. And then on the other side, we have an system view host application installed on our computer. So because we have an J-Link debugger onto the Nucleo board, we can establish the J-Link connectivity using a normal mini USB cable. So we can connect one end of the mini USB to the J-Link debugger on the board itself, and the other end will go to host PC, wherein your system view can capture the data from the J-Link debugger, right? And the system view API will be running into your microcontroller. I will show you everything, in the future and step by step. So let's go ahead. Now, let's just understand how the RTT work with a system view, because I think you may remember I said this once, that if you want to use a system view API in your microcontroller project, then you must have to have an RTT API as well. Okay, because system view API will be using an RTT API. I mean, it's basically uses the RTT technology. So what happens is, on the top, we develop an embedded application, right? So I have an embedded application, that's a main.c file. And in that main.c file, I have created 3 tasks. So the first task will be green LED blink, red LED blink, and third task will be an orange LED blink. So I have 3 tasks that I have created, and that will be written into main.c file, and that's my embedded application. Now this embedded application then talking to some sort of middleware and RTOS, because here in this case I'm using a FreeRTOS. So my main.c is talking to the FreeRTOS API, and then this middleware FreeRTOS API then can able to talk to a system view API. That's why we have to integrate the system view source file that we will download from the SEGGER website and integrate it in our microcontroller project. So we just download some header file and source file and then integrate it in our STM32 project into the Cube IDE. And then this system view API then talk to your RTT API, okay, real-time transfer API, RTT API. And that RTT API, as I said before, it will help to extract the data from the microcontroller and pass it to the system view API. And this RTT API then have an access to the RTT buffer. If you remember, we talked about it in the previous session, that the RTT buffer is the one where we collect all the data. And from there, this will be a J-Link connectivity, J-Link debugger connectivity. So from this buffer, you can call it as a software FIFO or RTT buffer, whatever you like. But from this buffer, it will be basically a part of target RAM. So our J-Link debugger will pull the data from this buffer and then send it to our host PC. That's where we have a system view. So I think this picture basically summarizes that system view API will be used along with then RTT API. So you must know how the RTT works in order to get to know exactly how the system view works. But basically, if you just want to use it in your application, you don't need to know everything from the basic. I explained because I just wanted to use the flow of the presentation to give you better detailed perspective. But I hope this makes sense. Now, let's just talk about the hardware requirement, because you might wonder, okay, I got to download a system view source file and then I got to download the RTT source file and then integrate in the microcontroller project. But what about the hardware? So if you're using and any kind of evaluation board, whether it's a nuclear board or discovery board, make sure you flash the J-Link firmware into your, if you're using an STM32, whether it's a Nucleo or the discovery board. And in case if you're using the official J-Link Debug Pro, that's a cherry on cake, because you then have a lot of exclusive features that you can use it, and it can also leverage on talking to the SEGGER software ecosystem framework. So you can have anything like a J-Link EDU, or maybe you can have a J-Link Pro or Ultra, or you can have a J-Link OB onboard firmware, J-Link OB, and that has not only to be found on to the STM32 evaluation board, but you can also find it on the LPC series, which is probably LPC Link or something, and then NXP, and then you will have with the Nordic some evaluation board. So just make sure whatever the board you have, just read the documentation and just find out if your board supports the J-Link debugger. So you can just flash the firmware and then convert it into the J-Link debugger. And one more thing on the hardware side, your microcontroller should be capable to have at least minimum 2 kilobytes of ROM. So it should have a 2 kilobytes of flash and 600 bytes of RAM. So it could be somewhere 500 to 600 bytes of RAM. So this is a minimum requirement, because what happens is when we port this files, SystemView source file and the RTT source file into our microcontroller project, it create a buffer. So there will be a buffer. In the buffer will be a part of your target RAM, so microcontroller's RAM. So it will eat the memory from your RAM of your microcontroller. So you just have to have this minimum requirement that you have to keep in mind. Okay, and the rest of the details you can find it on the SEGGER's documentation if you just want to find out if your microcontroller does support the J-Link debugger and this SystemView and RTT API. And if you're using an official J-Link debug probe, then you don't need to worry about anything. You still have to make sure this requirement of a memory, but you don't have to worry about the flashing firmware and all other things. It's just plug and play. You just connect and it starts streaming the data. So let's just talk about, as I mentioned, there are two modes, recording modes, through which the SystemView can able to log the data from the microcontroller. And the first way to record the data from the microcontroller is a single shot recording. Now, the single shot recording is very much of a manual recording process. Let me tell you how it works. So once we start debugging a microcontroller project, I hope everybody knows how to debug or how to enter into the debug mode of debug perspective of STM32. If you don't know, then please check out our previous videos, because we've been talking a lot about debugging from past 1 year and a lot of videos out there already. So in manual recording, we manually start the debugging, then we start capturing the trace, and then after a few seconds, we stop capturing the frame. And between start and stop the capturing process, we have a frame that will be stored into the buffer. So I would be calling as a frame, but it will be a data that will be stored into, let's say, an up buffer descriptor or something. And then we pull that data. So it's basically, if the debugger collects the data manually, then we have to export from our STM32 Cube IDE, say for example, in this case, because I'm using an Cube IDE for debugging. So from the memory view of the IDE, I have to export it to other software application. That's a system view, right? So it's very manual process. I will show you both process live. Okay, so don't worry. So the single shot recording is a manual recording process and can be used without J-Link. So that's a great stuff. Even if you don't have onboard J-Link debugger, and even if you don't have anything, you still can able to use a single shot recording method, okay, just to record the traces. The only caveat is, in the single shot recording, you can only log the debug information, limited information, because you can start capturing data and then you can stop capturing data, and between that you can only store that much of. You can't just log or record the data for a long period of time. That's the problem. So you can just capture the sample. So, and that is possible without even having a jailing. Even UART can be used for this. But I don't want to go in that. I just want to stay with the jailing debugger. So record data until the target buffer is filled. That's what I said. Like you have a buffer, and of course, if you have a buffer, then it has a fixed memory, and you cannot run out of that memory, right? So you can only capture a limited part of the traces, and it allow us to enable recording only specific part, because if we have to capture an event of a certain part of interest, then we have to make sure which timeline that we want to capture, or which event that we want to capture while we are recording the traces, right? So that's where the single shot recording comes in, right? So single shot recording is where you can record a specific part. So it's very useful when you just want to log a specific part of the debugging process, or maybe a specific event that you want to focus on. So that's how it is. Now let's just talk about a continuous recording. So continuous recording requires a jailing debugger. So you must have to have a jailing debugger. And then the recording, the great thing about it, the recording happens over a long period of time, because it doesn't rely on the buffer inside the microcontroller's target RAM, right? So you can then have a large target memory buffer, because it's a part of the jailing. And I think you know the jailing hardware is not cheap, right? They are, I would not say expensive, but they are not cheap. Okay, so I hope you get the point, the limitation of both of them. So both have an advantage and disadvantages, whatever you like, but I will be using a jailing onboard debugger onto the STM32 Nucleo board. So now let's just talk about what softwares you need in order to work with SystemView, and then what kind of source file that we need in the process of porting SystemView with our microcontroller project. And you can see this is a SystemView software. If you go to a SEGGER.com website, on the top menu bar, go to downloads, and you can have a SystemView. You can download the latest version, and down below somewhere you can able to see SystemView target sources, right? So target sources means this is the source file. This include some header file and C source file. This files we want to integrate as a part of microcontroller project. I will be showing you just in a moment. So let's look at this project. I will show you the live project, but in this slide, I want to put things in perspective. So I just want to take an advantage of the flow of the project. So once we download the source file from the previous slide, you can see here I have created a project SystemView in the project pan. And you can see I have created a folder called config. And in a config folder, I have integrated RTT configuration file, this header file, and then SystemView configuration file. Remember what I said. If you want to integrate your microcontroller project with a SystemView application, then you need to have an RTT capability as well as the SystemView API, both that you need. And then you can also see the one more interesting thing here. The next folder is an OS folder, right? And in OS folder, you can see I have added this C source and header file that has to do with a FreeRTOS. Now, you might ask this question, what if you are not using FreeRTOS? What if you are using some other real-time operating system? Let's say you are using some Micrium or maybe MBOS or something like that, or something, some RTOS which is not so popular, right? So for that, when you download the target source file, which I showed you from the previous slide, when you download the zip file, you just go to operating system OS folder, and you will have all the source and header files. Okay, in case if your RTOS is not listed, then you can just write it to the SEGGER, and they probably will provide you the port for your RTOS in case if you need any help. Okay, so that's how it is. FreeRTOS is very popular, so you can get it everything everywhere for FreeRTOS. Okay, if other operating system, then you have to do a little bit of emails and such and stuff. And then you can see other source file that I have added, and that's special features that we want to add. Let's say we want to add in our project a printf style API from the SEGGER. So that's why we have this RTT printf.c, and then there are RTT API through this RTT source file, and then SystemView API access through the SystemView. So I hope this is clear. Like we download this files from the config, OS, and the SEGGER, this is all a part of target source file, which we downloaded from the official website of the SEGGER, right? It's not something that we are writing any code by ourselves, right? We are getting all the source and header files, and then we are porting into our microcontroller project. And once we port this in our microcontroller project, then our project basically is ready to use with a JLink debugger, and then we can make use of SystemView. Now the question comes, how can we use it, especially in the single shot mode, right? Because in a single shot mode, remember what I said, most of the data capturing is a manual, right? So look at this picture here on the slide. I took this IDE into the debug mode, and onto the debug mode, you can see I went into the memory view of the microcontroller debug perspective. And here we have this RTT buffer. I will show you live. Just hold on for a while. And then we put the size of the buffer, then the start address and stop address. Remember what I said. We start capturing the data, so that's the address, and we stop capturing the data. So between you need to collect the data, and that's the data that we export into this svdat file. You see, I have named this file as a devheads.svdat. Now another question comes, why are we giving the name svdat, and what the hell it is? So svdat is basically a file format, which is very loosely defined file format. In the world of SEGGER's tool, you can name it as a svdat, which this file will store all the information, debug information, which later, so this devheads.svdat file, we will, once we export from the debug window, we will import it into the system view. Remember, the cube IDE, that's where we will be starting the debugging, is a part of IDE. And the system view, where we want to visualize and analyze the RTOS task, that's a different piece of software. So we are exporting this svdat file from the STM32 cube IDE and importing into the system view, right? So that's how basically it works. I hope this helps, but when I show you, it will be more clear, right? So let me not waste your time, and I will take you to the project. Otherwise, okay, let me just talk a little bit about the system view, how the system view looks like. So basically the system view is made up of a lot of different windows. So you can see there is a context window. So here's a context window, so we can see all the FreeRTOS tasks that I have created in my application. Then you can have a log, which will tell us whether the JLink debugger is connected, disconnected, started recording, stop recording the data, all the fancy stuff. Then we can have a timeline where we can see the task execution and all stuff. So this kind of windows is what we will be expecting. So let's go to the project. So I have this STM32 cube IDE, and I have created this system view project in the project pan. Let me connect first STM32 nuclear board. And if you remember, just open a device manager. Once you connect, go to device manager, go to port, and make sure you have flash the JLink firmware on your STM32 nuclear board. And if you don't know how to flash the JLink firmware, means how to convert ST-Link into JLink, you can refer to the previous engineering hour episode about RTT, because that's where I have showed you step by step, open the JLink terminal and then run some command and convert it into the JLink. So now here the JLink is enabled, so I don't have to worry about it. And then I go to my IDE, and here's the project that I have created. Let me just enable. Okay, sorry. So here's the project system view, and you can see this is the config folder. That's where I explained this before. We added the configuration for RTT and configuration for system view. And here's the OS related files. Then here is the other source file for other SystemView API access in case if we want, and of course we want, so we ported this files here. And then in the project, you might wonder what I'm going to showcase today. So I have this green LED blink task, which blink the green LED 10 milliseconds. This task will blink the LED after 10 milliseconds, and then there's a red LED blink which blinks, which task executes after 20 milliseconds, and orange is basically a 30 milliseconds. So just remember these things. Forget about LED blinking and stuff like that. Just remember things. We have a 3 task. The green LED task will blink LED after 10 milliseconds, red LED will blink 20 milliseconds, and the orange LED task will blink it 30 milliseconds. Okay, 10, 20, 30. Because this is what we're going to be visualizing when we will be analyzing our project. Okay, the debug information. So let me just build the code and see if I have any error or warning. So there are 0 error and 0 warning. And so you might ask this question, like, how can we ensure that our project has the SystemView API been integrated into the file? So in the main.c file, look at this. If I scroll down, you can see just the 2 lines of code. You just have to add 2 API, and that 2 API are SystemView config, SEGGER SystemView config, and then SEGGER SystemView start. So this basically API. So the first API will configure the project for the system view. It prepare the project for system view application. And the second one is to start the system view so that we can have an ability to start recording and stop recording the traces, right? So just the 2 lines of code that you have to add in your project, and you have to port the source file, and you're done. Okay, that easy it is. So as I built the code already, let me just click on the debug button here on the top menu bar, and make sure your jailing configuration is done into your debugger. So the moment, because my nucleo board is already onto the jailing debugger, it asked me whether I want to accept the terms for the jailing. I would have to say accept, and then say okay. This happens. Let me just click on debug again, and this time it will work. Okay, so it's just a known way, that's the way embedded system works. So look at this. As soon as I enter into the debug perspective, into the expression, you can see there's a SEGGER RTT. This is the buffer I was talking about, and let me expand this to show you. And there is this buffer like up buffer, and in up buffer, if we expand this one, you can see there's no data because we have not yet captured any data. Okay, so let's say if I want to capture the data, look at this. The buffer size, the size of the buffer is 0, so there's no data captured. I will show you live how to capture. And then the buffer data is literally nothing. Let me capture. So let me click on this run button in here, and I would take some time, and even I can open the system view for you. So this is the system view application, and if you wonder, this is how it looks. So click on continue, and this is basically from the previous one. Maybe I can say close. This is from previous one, so don't worry. I just to show you from scratch, let me just suspend temporarily just for a few seconds, okay? Because we just have opened the system view, and because we have the jailing debugger connected, we can go to target and start recording, right? But we cannot start recording. I mean, it's a good practice first to start recording traces, and then we can accept. Okay, and look at this. It's try to record, and because I have a jailing connected jailing debugger, it will automatically detects and start reading data in a continuous mode. Can you see this? This data starts streaming, data starts coming. Let me just stop for a while so that you can see it. A lot of data came up here. So you can see the start event, and then the first task executed was a green LED task, right? Look at the code. If we go to main.c file, the first task will execute because it's a 10 milliseconds, right? The second task, after another 10 milliseconds, we will have the red LED task will execute. So, and then the orange LED task. So let me take you here, and if I scroll down, You can see after green, there's a red LED, and this information is with the timestamp, by the way. Okay. And you can see this events, all the events has been logged. So let me show you the beauty of this. Let me expand this. So I just hold on. Okay. I can't explain so many things because this is very, very comprehensive tool. And you might have seen, like when I move this window, this is called a timeline window where we can visualize our task. Can you see this? Let me show you magic. Let me start capturing the traces live, and look what happens. Because it's a new capture event. So this is a continuous recording mode, by the way. Click on accept. And now you see the event start login, and look at how many, I mean, I can't even name it. And you can see everything is live. All these windows are updating, right? Oh, I have to stop, otherwise too much data coming. So you can just zoom in, and you see when I move, let's say if I select a particular task. So let's say this is our green LED task, right? So when I select green LED task, it will come to the green. Look at this. When I click here, it will go to this green. You see this marker come to the green LED task. And the one reason why I love SystemView is it has this color coding, right? So you can, through the color code, look at this. The green LED task is a little bit, I don't know in English what the color name, whatever it is, but you can quickly notice, right? So let me just take the next red LED task into the context somewhere, and you will see the marker will move. So you can basically, this way you can analyze it, and you can see there's a timeline, like how many milliseconds, how many microseconds your task is executing, right? I don't actually have that much of time to spend here, but as soon as I click on red task, you can see the marker will go to this pale, whatever yellow color. I don't know what to call this color again. I don't have English word for it, but you see the red task. Look at this one, because I selected the red task. So what I'm proving my point is, this context window is in synchronization with this timeline window. So everything is a real time. Remember, I used this word on my slide, real time and runtime behavior. So everything is happening live, real time. Okay. So this is a continuous mode. A lot of information that you can able to get, and I would not lie, you need to spend some time to analyze all this windows and understand there are crazy features here. You can use this trigger, and you can see you can, if you want to trigger the the event on, let's say you want to take the marker on the green task execution, you can select it, and then you have a run, and then you can hit the button, and then you can trigger the event. So a lot of crazy feature which maybe we will cover in the future, like advanced system view, something something, right? Some engineering hour. But this is basically how you can use this context window of a system view to analyze your task, and how you use the timeline. Now I want to talk about this timeline, because this timeline update in a real time, right? You probably have seen. Let me create some space here. My screen is not very big, the laptop screen, but I will try to fit everything, to put things in perspective. So look at this one. Let me again capturing the live data in a continuous mode to show you some more magic. You see this traces timeline is updating the task execution in a context of the number of event for every single event, right? And then you can also see there's another window here. It's called CPU load, and you can see that also analyzing the load of an CPU microcontroller live. And let me show you some more data here, which you might be surprised. So application name, the RTOS your application use, in case if you have the project you don't know which RTOS, it can be told like this. And then the target microcontroller, what frequency it is running, how much duration. So far I wasted your 45 minutes, 45 seconds to capture this data, but I wanted to show you, like, you can literally capture the duration, also a number of events. It can also tell you how many tasks that you log the information with. So in our case, it's a 4 task. Of course, you would say like green, red, and orange LED. Then why the fourth one? The fourth one is basically for the Sysdig, because I'm using Sysdig to run the FreeRTOS. I forgot to do it for the RTOS aware debugging, but I want to create a dedicated session for the RTOS aware debugging. But you can see how much information you can get. I mean, you can just dream about it if you do not have this kind of application, right? And this all things are visual. Like, I'm not a huge fan of this black terminal windows, and I would prefer something more visual. So let me show you. So let's say this is your CPU load, right? And when you are analyzing your RTOS behavior, and you can see the load shows very clearly with the color codes, right? And you can, through the color codes, you can quickly analyze it, which task, when certain task is executing, how much load it creates, and how the context switching is happening, and how the CPU is handling all the task switching and task execution, by the way. And you can clearly notice in case if there is any inefficiencies, or maybe if certain task or certain event create a lot of load in your controller, especially a battery operated products, right? So in the battery operated products, certain task consume, while certain tasks execute, maybe you have some instructions, some code which consume more power and create a load. So you can literally track down everything and optimize your code further. So that's about CPU load. So I think I cover pretty much all these windows, right? So one is a runtime. So this will give you the runtime context of how this task uh, change its context execution. And then there is a context like how and for how long your task has run. So by the way, because these are like a lot of information, and it would be very difficult for me to speak for 1 hour and explain every little thing, but you can also have a look into the system view documentation from the SEGGER. It's very good documentation that they have. So you can basically find all the explanation for every window of this, and you will get all the information that you need that will help you to analyze your RTOS-based real-time application. The log window, you remember I said it shows you everything, like the jailing connected, disconnected, started recording, stop recording, everything you can able to see it here, right? So the log, and the terminal will show you all the information going into or coming out from the microcontroller into the terminal log. I hope this pretty much sums up all the windows. And so far I have showed you how to record the data in the continuous recording mode of a system view. Okay, so this is how we will live analyze the data. Now, before going to system view, I was talking about this buffer. And sorry for that. I planned to talk first about a single shot recording first, and then I wanted to go to continuous recording mode, but I think life has a different plan. So because I had a jailing, so it started throwing data live. So I thought maybe let's just use it. So let me just talk about how you can export this debug information. Now, you remember previously when we were talking about this, when I took you here, this was empty. This information was 0 0 in the beginning, especially this up buffer. And if you have attended my previous session RTT, you probably know that what is an RTT up buffer. This is the buffer where we basically store the information, especially the one that we want to send it from the microcontroller to the host PC. Okay, and now you see this is not an empty anymore. This has some log recorded. Look at the size of the buffer, 8096, right? So we want to capture this buffer, and then we will export it into our system view to analyze. Okay, because so look at this one, this start recording traces for some time and suspend the recording traces. Now I have, let's say, a new piece of information into my buffer here. So to export this data, as I said, we have to go to window and show view, and we have to search for memory. So once we come into the memory view of the debug perspective of STM32Cube IDE, then we have to click on this plus button here. And believe me, this step-by-step process is nowhere on internet. So here we have to put the address. Where the hell, from which start address? And look at this one, like this buffer. So this buffer, follow my mouse cursor here. This buffer start at this location, memory location. And I have to type because I forgot to copy. So 0x2001 369C. I hope this is right. Let me click on OK. And now you see in the memory view, this register been added. This buffer, I mean, the memory location been added from the memory of the microcontroller. And you see this data, captured data in some crazy format. And we have to export this. So to export from your memory view, you have to click on this button here, this crazy little button called export. So click on this export. And now we have to put the size of the buffer. So the buffer size is 8096. So we have to put this 8096 here. It's already there. I don't know why, but if there's no information there, you can just type it by yourself and it will automatically get the start and stop address from this debug information that is captured on the expression. And now, because I capture the fresh new event, and remember what I said, when we export manually this debug information, I will have to store this information with the file name DevHeads 00, let's say 007, James Bond, and .svd format, right? So remember I said like this information will be stored and exported into sv file format. And this file will be generated into the SystemView folder, which is on my desktop and on STM32 project. I try to show you. So this is that STM32 folder on my desktop, and let me show you. This is the system view, and look at this here, right? There is no sv.00, whatever the file name that I have given. I forgot 007. So let me click on OK, and look at this. It exported the address and the memory. Let me take you to the file, and look at this. The file is created, right? devheads007.svdat. Now we go to our system view, because here we are using in single shot method, so which is a manually capturing event. So I am going to go to file in the top left menu bar, then click on load data. And now I'm going to select my file, the data that I have stored into this devheads007.svdat file. And then I'm going to click on open. And look at this, it's, oh no, what happened? I don't know. Let's just click on OK and see what we get. Okay, so we have this trace data, system description, name. I think something went wrong, but you still can see, look at this one, the system description, right? This should be DevHeads demo project. Something has to come, right? Because in the project we have configured it like that. And because I don't like things like this, I would again capture the trace. I can stop. I can go to memory and quickly export the fresh piece of data, right? Sorry for that. That's live, you know, doing live is crazy. This time I would give 0022 is my lucky number. So let's click on OK. And let me go to system view and try and load this new data. Oh, it crashed. It's because this is not running. So Sorry for this. I have to load the system view. But in the first place, when we created this 007, then it was it did got it. Look at this one. Like name is a DevHeads application, which basically we get some crazy stuff here. So let's go to file, and this would basically, because here the debugger wasn't the captured event wasn't captured properly. So whether I think not enough data that we have captured. So once that's there, maybe I would just stop sometimes, because this is a manual way of exporting this data. And maybe I would export it. And I will save it with the same file name. Just make sure the buffer size, because we are running very fast. This is very big topic, by the way, believe me. So let's first start. I mean, if the target is connected, no, we don't want to, let's say, read recorded data. So because the target is not connected, maybe that's why. So I would just connect the jailing debugger. Now I would go to load file. I would stop. Oh no, this is crazy. Load the system file 002, and oh, it's crashing again. But maybe I have to disconnect the nuclear board, and I have to open system view. So this certainly load the file. I think I have to connect again, and I have to completely stop debugging. I'm sorry for that, but this happens, right?
Yeah, of course.
And this is not, yeah.
While you're doing that, I just wanted
Yeah.
to remind everybody, throw some questions over into the chat channel or into the questions tab. One of the questions I'm going to ask Umesh when he has a chance to get his bearings are, about SEGGER versus other tools, like things that are available from like Percepio, like Tracealyzer. If you're all working in embedded development, I'd like to hear from you what you guys are using. If you're using SEGGER, or if you're just getting started, any questions you guys have, load them up now, and we'll get to as many of them as we can in the time that we have remaining.
Yeah.
But yes,
So,
live demos are tempting the gods.
and this is like involves so many steps, so it's not something that you can flip the button and so this time I would capture this address. So I will use a copy and paste and not type anything by my hands. And maybe I have this memory location now. You see the data, which I would export. And let's just make sure the buffer size is 8096 and start address 2001369. Like, let's say, let's just okay. Let me just. I just copied the buffer size because a little conservative approach. And this will be all 30 this time. And yeah, and make sure you select the raw binary format, by the way. Export it. And then in the system view, file, load data. And then you have it working, right? Look at this one. DevHeads application. It's a free authors. 16 megahertz, everything detected properly, right? And then click on OK. And because it's just a little trace, right? We just capture event. That's why you don't see much here. But if I can just take it to this captured event here, you can basically, let me just take this. Why this? I cannot select this to stretch it up. That's a crazy part of life. And maybe I would just use a manual zoom. Okay. And I hope you all will trust me. Look at this. The first task execution is a green task in the captured event. The second one is a red task is executing, and then the orange task is executing, right? And if we analyze further this recorded trace, okay, now it's working. So let me make a little bit of big view. Okay, let me zoom out to show you something really interesting. Okay, just look at this one. So because the green task is executing after every 10 milliseconds, so 10 milliseconds, 10 milliseconds, so there are 10 milliseconds. And then we can expect at the third one the rate to execute, because 10 and 10 20, so the rate will execute, and meanwhile the green will pop up. And the next one, look at this one, after the 30 milliseconds the orange will be executing here, right? Look at this one. And as soon as the orange will be executing, then the scheduler switch the context, and then you see again, because again another 10 millisecond will be elapsed, and then you have a green LED task is executing, right? So that's exactly what we wrote in our code, if you remember, in our project file, right? Let me just stop debugging and then go to the code. And this was the behavior I was saying. Like, so when the red LED task will execute, obviously there will be a 2-time green LED blink will happen, right, in the 20 milliseconds. And the one orange LED blink happens. Between that, you have 3-time green LED blinks, 1-time red LED blinks, right? That's exactly what we have seen the behavior when we were analyzing the task. Oh, I hope we are not running out of time. We are running out of time. Sorry for this. I can quickly go to presentation, and I hope you have seen it live. And yeah, so let me just summarize things pretty quickly. What are the advantages we have with the system view? We have a minimal system intrusion with the CPU independent into the microcontroller. We don't need any additional pin, because if you use a jailing debugger, whether it's an onboard or official jailing debug probe, it uses SWD and the standard JTAG debugger. So you don't need any special pin to sacrifice in your project. It supports RISC-V devices, which allows system bus access into the microcontroller architecture. And the use cases where you can use system view, it will be used for analysis of a complex embedded systems, which basically have a multiple threads and complex events and complex API trigger, user event. Basically, if you want to track down a lot of things, you can able to do. Then you can also verify the system behavior. When you build an application, you have some real-time requirements, and you have to make sure whether your application meets that real-time requirement. And that can be only done by analyzing and recording the traces, and then analyzing whether at what milliseconds, microseconds your task execute and what happens into some microcontroller. And then you can optimize the resources and the performance. I can talk about it for another 2 hours, but I think we are running out of time. So thank you very much for being a part of this live event. And I'm looking forward to get the question if there is any.
Yeah, the one question that I had on there, and it's really quick because we're almost out of time, is tracealizer, things like that are really RTOS specific. Does SystemView and the SEGGER portfolio in general have anything that allows you to view things down to the granularity of what's happening inside mutexes or semaphores, like really RTOS specific function analysis?
Yes, why not? You can able to do it, and that's a part of, I mean, if you set your project for RTOS aware debugging, and then you can pull all the RTOS specific as you likely probably have already seen in my slide that you can basically get every resource of your embedded system, right? And that also includes the mutex and all other things, whatever, as a part of your RTOS, right? So it's possible. Why not? But just remember, to get this information into your debug trace, you have to enable the RTOS aware debugging feature, right? And if you wonder where the hell it is, let me show you. Just open your QIDE, and then you go to your debug configuration setting here. Somewhere in a debugger setting, you see the RTOS kernel awareness. And if you enable this, then you can have an RTOS proxy, and then you can use the driver for what. Let's say my project uses FreeRTOS, so I can use it FreeRTOS. If somebody uses ThreadX, they can use a ThreadX, right? I hope this answers in detail.
Yeah, for sure. So that's it for today. I did want to give Umesh a couple of seconds to talk about what's going to be happening next week. I've dropped a link to sign up for the next session, the third in this three-part series on SEGGER Debug. What's coming up next week?
So in the next week's engineering hour, we will be looking at another tool from SEGGER called Ozone. And Ozone is really a great tool to do an instruction tracing and code coverage and code profiling, which is very, very advanced stuff in the world of debugging. So basically here today, we saw how to optimize, visualize, analyze your embedded system. In Ozone, you can literally get the information from your microcontroller in a real-time system where you can optimize and prepare your code even for certification. So the extracted data that you log, you can submit to get your product certification even, right? So great stuff. I'm not saying everything is easy, but I think these are very, very important thing in a professional development, product development.
Great. There is one quick question about Zephyr RTOS support. Do you know whether or not SEGGER is supporting Zephyr yet?
I'm not sure because, but I think we have an awesome people in our community about Zephyr. So why not use this opportunity and post this question? But I haven't seen much. Sega started supporting Rust, that I know, as a programming language, but not about uh, Zephyr as an RTOS. But maybe,
Okay.
who knows?
Yeah, Mert, why don't you check out the Discord community? Just go to discord.gg/devheads and ask it in there. And I know there are several people working with Zephyr right now. Anyway, I'm out of time. I really appreciate Umesh. Great stuff as always. Thank you so much. And then we'll be back here next week at 1500, same time that we started today, to talk about Ozone. So we'll see you in the community. Thanks so much, and have a great weekend, everybody.
Thank you very much. Bye-bye.